Hello everyone, welcome to another lecture on isotope geochemistry. In the previous lecture, we discussed about some of the basic aspect of nucleus. We talked about electrons, protons and neutrons. We also computed the mass defect, and that mass defect we translated into binding energy. For any nuclide, if the binding energy per nucleon is higher, then it is a more stable nucleus. Today we will discuss more about the nuclear stability and also different modes of decay which brings a nucleus into stable phase. This is a very famous diagram about the abundance of elements in the solar system. We will discuss this also in the next lecture when we discuss how elements are formed, but generally these numbers are reported as normalized to silicon and assuming that the silicon abundance is around 10 to the power 6. If you see the curve more critically, you will observe there are a lot of seesaw kind of patterns that is observed in the elemental abundance in our solar system. Most importantly, you should be able to notice that the hydrogen and helium are the most abundant ones. So, these two are the most abundant element that you find in our solar system. Interestingly, there is a dip for lithium, boron and beryllium, and if you look for any element after carbon, there is an exponential decay in the abundance of elements in our solar system. To notice some other trends here, you will see that the iron abundance is exceptionally abundant. If you compare to the background value of this declining trend, then the iron concentration is high. And there is another point that we must notice is for some reason the fluorine concentration is lower in our solar system. Two elements which is natural occurring, but still we do not find them in our solar system are technetium and promethium. So, these two elements are not seen in our solar system. You may find these elements in some of the older stars, but not in our solar system. And also we see that the lead abundance is greater than expected. So, this is again an increased value for lead. So, all these seesaw patterns and the exponential decline in the abundances are largely linked into two things. One is origin pattern of these elements, and second about their nuclear stability. Now, about the origin, these elements to start with have formed either in a big bang or in a stellar nucleosynthesis processes or subsequent capture of neutron or protons in the extraterrestrial space or inside the star. So, that we will discuss in the next lecture, but today we will talk about nuclear stability. Some nucleus are stable, some are not, and we will try to understand why they are not stable, and also try to understand if they are not stable, how they try to achieve the stability, what are the pathway through which they can reach to a stable phase. So, if you try to understand the amount of nucleids that we know, around 2500 nucleids in the natural system, and out of the 2500 nucleids, only 270 are stable, only 10% is stable. That means nuclear stability is actually an exception rather than a rule. Mostly we find unstable nucleids, but there are only about 10% of nuclei which are stable. This is a compilation of around 2500 nuclei that we find in the system, and the black one are the stable isotopes and the other colors represents beta plus, beta minus decay, alpha decay, fission process, proton capture, neutron capture. These processes are written here. This line, the straight line is the n is equal to z line. So, this is the neutron number, this is the proton number. So, in the lower side most of the black points which are the stable isotope fall near n is equal to z. So, you have the same number of protons, same number of neutrons in a nucleus. But as you go to higher side, where proton, if you increase, they will start repelling each other, and you would like to hold them through nuclear energy, and for that you need excess neutrons. So, the most stable isotopes are actually those which has a higher neutron and lesser number of protons. Now, how much higher and how we know that which of the isotopes are stable? So, for that you need to compare all the isotopes. This is a table where stable nuclides are shown, right. So, Z is actually the protons, N is the neutrons, A is the mass. So, if there are even number of neutrons and protons inside a nucleus, then they are the most stable nuclides. So, among all the 250 stable nuclides, around 160 of the nuclides have even proton, even neutron numbers. And if the protons are even, but neutrons are odd, then around 55, another 55 stable nuclides are observed. If the protons is odd and the neutrons are even, then around 50 more are stable nuclides. And the least stable nuclides are the odd ones. So, the odd number of protons and odd number of neutrons are there, then you find the least number of stable nuclides. So, to have a more stable nuclide, you need to have higher neutrons and also even number of neutrons and even number of protons. Here is an example for calcium isotopes. Okay. So, calcium has several isotopes, and I have plotted these are the mass number for calcium isotopes. So, the calcium atomic number is 20, the neutron numbers vary from 15 to 33, and hence you have a lot of isotopes, and the abundance is plotted in the y axis, where these abundances are plotted in log scale. So, the abundance vary actually around 4 to 5 orders of magnitude. Now, what we see is the most stable nuclide of calcium is have the atomic number 20, then the neutron is also 20. So, this is the most stable isotope of calcium which has both proton and neutron, which is an even. Then comes 41, you do not have any stable radionuclide stable isotope of calcium, because they have odd number of neutrons. Same, you do see that whenever there is a odd number of neutrons, the abundance is either less or they are not stable at all. Whereas, we do see that whenever there is a even number of neutron, they are the stable. And an important aspect is, if you look for 48 if you see, number of protons is 20, number of neutron is 28, although they differ in the NZ stability curve, n is equal to z, they are very off from the n is equal to z line, still it is a stable isotope, and that shows the importance of even number of neutrons and proton in a nucleus and their stability. There is another aspect which we must discuss, is just not about having excess neutron to balance the electric repulsion between protons. It is not just about the even number of protons or neutrons inside a nucleus, but there is another interesting factor which is responsible for nuclear stability. We are not going into the quantum mechanical explanation for this. Even the liquid drop model cannot explain the the magic number, but to keep it in a qualitative sense, the magic number like 2, 8, 20, 28, 50, 82, 126. If a nucleus has these number of neutrons, then they are found to be very stable. So, the isotopes and isotones with magic numbers are unusually common. You do find lot of isotopes with having this magic number, which are very common in natural settings. Also, it is common, and also the nuclides are abundant in nature. Their concentrations in the natural system is also higher. They are very stable, and hence they have a higher concentrations also. The heaviest stable nuclide that you find has a neutron of 126, which is the one of the magic number. The neutron capture cross section for magic number are anomalously low. What is a neutron capture cross section and what importance it carries? So, every nuclide will have a cross sectional possibility where they can capture highly energetic neutron and transform into another isotope. If the capture cross sectional probability is higher for a nuclide, then they will go through transformation. But for those elements, those nucleus with magic number have the lowest possibility of getting transformed through neutron capture, because they have a less capture cross section probability, and hence these are the reason they are stable, and also they do not go through alteration quite readily. Now, we know under what scenarios a particular nucleus is stable, but as we discussed also that nucleus are mostly unstable and there are very limited amount of nucleus which are stable. We will now discuss how these unstable isotopes go into stable phase. Now, the decay of unstable isotope may occur through alpha decay, beta decay or gamma decay. First, let us discuss what is a gamma decay. A nucleus which is in an excited phase or unstable phase may release a gamma ray, which is nothing but a high energy photon, it is a electromagnetic radiation. Now, that nucleus may release an energy through a gamma radiation and reach to their ground state through the gamma emission, which are typically of hundreds of keV. Example is, let us say any isotope in an excited state, the star represents the excited state, can go to the same nuclide but more stable through decay of, through release of a gamma radiation. Often these gamma radiations are linked to a alpha or decay series. So, let us say there was a isotope which went through a alpha decay, reached to a excited phase because of the energy balance, and now that excited unstable nucleus will release a gamma and go to stable phase. Similarly, it can happen for a beta particle also, and often that gamma radiation is quite immediate. It is in the time scale of 10 to the minus 12 second. It is not always so rapid, but mostly in 10 to the minus 12 second there will be a gamma decay subsequent to alpha or beta decay, and they will reach to a very stable phase. The other decay mode is alpha decay. Now, what is a alpha decay? It is basically a release of alpha particle, which is nothing but a helium in the nucleus. Now, because it is a helium, and if you see the neutron and proton number, so if you have a parent which is unstable with a neutron number of n and proton number of z, atomic number of z, if there is a decay of alpha particle, 2 neutrons is lost, 2 proton is lost. So, it will reach to a daughter which will have n minus 2 neutron, z minus 2 proton. So, effectively there will be a loss of 2 He4. So, decreases the mass of daughter by mass of a alpha particle, plus the kinetic energy of particle and dot nucleus. So, the energy has to be balanced and the matter has to be balanced. So, they will decrease the mass as required for a alpha emission and also the kinetic energy that must be taken care of. Nuclears having atomic number more than 58 often go through alpha decay. It is not that all that has atomic number more than 58 has to go through alpha particles, but the unstable nuclide more than 58 often can go through alpha decay. There are few exceptions, but mostly they are 58 plus and unstable. There is a possibility that it may go through alpha decay. And each alpha decay is associated with some energy. The decay energy associated with alpha emission has a inverse correlation between energy and half life. So, higher the half life, less is the energy, less is the half life, higher is the decay energy. So, this is what. Here is an example of alpha decay. Let us say 92 uranium 238 decays to 90 thorium 234, it releases a alpha particle, and because it does not directly reach to the stable energy phase. So, it releases a gamma radiation and have a decay energy. The energies of alpha particles vary between 1.8 to 11.7 MeV, they are very high, it is in the MeV scale. You remember in the gamma radiation we talked about hundreds of keV, but in case of alpha decay the energy associated are mostly 4 to 8 MeV, but they range between 1.8 and 11.7 MeV. Of course, we discussed that the energy is having a inverse correlation with the half lives. Another important concept here need to understand is recoil effect during alpha emission. Newton law, we know every action has a reaction. Now, if you release a high energy of MeV level, so there is a nucleus and alpha particle have gone out, through that recoil the product will have some energy and that is the recoil effect. So, alpha decay imparts appreciable recoil energy to the product nucleus. Now, let us say if you assume that 238 uranium through multiple chains, let us say it reaches to 234 uranium, and let us say you have a lattice and there was a uranium 238 to start with, and after decay you now have 234 uranium. Because there was a release of alpha and there is a recoil effect, this 234 uranium at this site is not stable as it was for 238. Now, stability of an element inside a mineral is largely linked to the elemental behavior, not the isotopic behavior. That means 238 uranium or 234 uranium both should have same stability. But because there was a recoil effect and 238 decayed to 234 is less stable at that phase. So, if you erode them and if you erode this, more of 234 uranium will come compared to 238 uranium, and that is because it goes through recoil effect. This is a very important concept and we use this to find the depositional timing for oceanic sediments, where the more labile phase of uranium 234 because of the recoil plays a very important part in dating oceanic sediments, oceanic carbonates basically. This is only true for alpha where MeV level of energy are involved, not for beta particle, mainly because the energy associated are limited and hence they do not play a larger role in terms of recoil for the product nuclei. The energy, recoil energy depends on kinetic energy of the alpha particle that is emitted, what is the kinetic energy for that, and mass of the product, whatever the product is produced, what is its mass. So, basically if you write the energy, recoil energy for any element, it will depend on kinetic energy of the alpha particle mass of the alpha divided by mass of the product. To give you an example, 238 uranium emits energy in 3 sets of kinetic energy. 77% of the energy goes in the mode of 4.196 MeV, 23% goes in 4.147 MeV, and 0.23 almost negligible part of the energy also comes in 4.039 MeV. Now assume this 238 decayed to thorium 234, and we need to calculate what is the recoil energy imparted on thorium 234. We can use this expression, the energy is equal to kinetic energy for alpha, which is 4.196 MeV, mass of alpha, let us assume it to be 4, divided mass of the product, let us assume this to be 234, I have rounded it off. So, the numbers is 0.0717 MeV. So, if you are reporting the actual kinetic energy associated with uranium 238 decay, you should not only report the alpha energy, this is alpha decay energy, right. You need to add also the recoil energy, which is 0.717. So, the total energy that is involved with the decay of 238 is 4.268 MeV. Now, coming to beta decay, unstable atoms decays by emitting a negatively charged beta particle and also a neutrino, right. So, basically what happens during beta is electron is expelled from the nucleus, there will be a change in the charge, but the number of nucleon will remain the same. In case of a beta decay, the unstable nuclei decays by emitting a negatively charged particle, and to balance the energy it also goes through an emission of neutrino. Here is an example of iodine decaying to form xenon, and it also emits a beta particle. So, if you see, there will be 53 is the atomic number which transform into 54 because there is a -1 charge is associated with beta, but there is no change in the mass side, the mass remains the same. Another example is this, where 24 sodium decays to 24 magnesium with a beta particle, associated neutrino and gamma radiation to balance the energy. Beta particles emit kinetic energy. So, beta decay series is not a monoenergetic. So, if you see the energy, it will go through, it follows a distribution, and there is a maximum beta energy that is generally reported. Beta particles emit kinetic energy equal to 1/3 of the maximum energy. It is a 1/3 of the maximum energy, and only a small number of particles have the maximum kinetic energy actually. So, if you see this plot, this is the beta particle energy distribution. So, it will follow a distribution, it will have a maximum energy. So, the average beta energy is about 1/3, and the remaining amount is actually taken care by neutrino or gamma radiation. Neutrino has no charge and a very small rest energy. Another important aspect is electron capture. So, it is actually reverse of beta decay. An electron is added to the nucleus. Okay. An electron is added to a nucleus to produce a nucleus with less mass than parent. The missing mass is carried off as an energy by neutrino or gamma radiation. So, an electron will go and sit on the nucleus, and there will be a release of energy. So, the mass will reduce, but actually the energy will be emitted through either neutrinos or gamma radiation. One important aspect which we have to understand is, in a radioactive decay series, they do not depend on temperature and pressure, we will discuss that at a later stage, but in case of electron capture, pressure can play a minor role, because pressure forces the inner electrons closer to the nucleus and increase their capture probability into the nucleus. That is why a small role of pressure is linked to the electron capture. Now, because there is a inner electron lost, there has to be replacement of that electron, and during that also we release lot of energy. So, these are the ways through which you balance the energy. Another aspect which is crucial is spontaneous fission. Like if you have a big liquid drop and if you give a small perturbation, they will split into two. Often this big liquid can split into two pieces spontaneously, or you give a small perturbation to split them. This is the role of a spontaneous fission process. Nuclei having high atomic numbers disintegrate spontaneously, or you may induce that, and form isotopes of two fission products. They may have a comparable mass. So, one isotope will split into two, and these two splits may have a comparable masses. Half-lives of fission decreases with atomic number. From thorium, which is in the order of 10 to the power 18 years, for CF it is 10 to the power 6 years. And if you write an expression for fission energy barrier, what is the activation energy needed to initiate a fission, that depends on Z and A value, and this is a plot that shows the activation energy and mass number. You see that with mass number the activation energy required decreases. So, the activation energy required for nuclear fission decreases with increase in the atomic mass. Higher the mass, lesser energy is sufficient to initiate a fission, whereas if you have a lesser mass, but it must have a certain number of mass to trigger the fission, but in that zone 200 to 240 zone, lead will require higher energy to initiate a fission, whereas compared to that of CM will require lesser energy. But if you compare that for lead isotopes itself, that sort of look that follows a reverse trend. Isotopes of particular element decreases with the decreasing mass number. So, these are the important observations. Now, fission is a very important aspect because we are constantly looking for alternative energy resources, and nuclear energy is one of them, because if you initiate a fission, they can give you energy that can be very high. So, fission is a very good alternative for energy resource. Slow neutron fission can induce uranium-235 fission. So, it requires lesser energy, it can start a fission process, whereas if you are looking for 238 isotope of uranium and its fission, you require more than 1 MeV energy. In case of uranium-235 fission, product nucleates will have mass number that varies from 72 to 167. Once these fission products are produced, they are often produced with excess neutron, and they decay through negatrons, and they do that till they reach to a stability. And during this process, lot of neutrons are also released, and that has an energy varying from 0.05 to 17 MeV. Now, as I mentioned, this could be one of the important nuclear energy resources. It releases about 200 MeV as a result of induced fission of single 235 uranium. So, if you just trigger a fission process for uranium-235, one single fission of uranium-235 will produce about 200 MeV, and that is the basis for most of the nuclear reactors, where uranium-235 or any of such isotopes are used as a fuel, and there will be fast neutrons or slow neutrons which will be supplied to induce a fission, and moderates which can control the reaction rate inside the fission chamber. But the concern with this nuclear energy is the amount of nuclear wastage that is creating. Although it can give huge amount of energy, but it can introduce lot of radionuclides to the ambient environment. To give some number, the weight of uranium fuel that are used in US in one single year, let us say 2000, exceeds 40,000 metric tons. Now, this after the fission is done, this much of wastage are temporarily stored in 100 reactor sites, and that can be very tricky. We are still not prepared to control the nuclear wastage, and that sort of is the limitation using this nuclear energy resource for normal usage. So, here are few reading materials for this particular lecture. The aspect of nuclear stability, decay mode and radioactive decay is well described in this book on isotopes and principles and applications by Foray, and also some description is given in Isotope Geochemistry by William White. So, these are very good interesting books. Please read them to clarify what we discuss in today's lecture. Thank you.